Hello? Hello? Can you able to see the whiteboard?
Yes.
Okay. So what is been given in this particular problem is there is a 100 mm pipe that will be used for carrying the steam at 160 degrees Celsius. It is planned to lag it with 100 mm preformed insulation. The outside air film coefficient of the lagged pipe is estimated to be 5 watt per meter square degree Celsius, and that from the bare pipe at 160 degrees Celsius would be 20 watt per meter square degree Celsius. The thermal conductivity of the insulation is a function of temperature. K is given as 0.9 plus 3 into 10 raised to the power minus 4 into T watt per meter degree Celsius, and temperature is in this equation is in degree Celsius, and the ambient temperature is 30 degrees Celsius. If the estimated insulation cost is 15,000 rupees per meter cube, including installation and the other expenses, and the steam cost is rupees 750 rupees per ton, calculate the payback period assuming rate of interest of 0.18 rupees per year. Latent heat of steam is given as 1825 kilojoule per kg. Okay. So I have just copied this problem from the tutorial sheet, and therefore at several places these superscripts are not appearing correctly, but you can directly see the tutorial sheet which is there in the MS Team. So there it is correctly written. Okay. Is it okay to everyone? Hello.
Yes, sir, it's fine.
Okay. Now what is being asked in this particular problem is there are two cases. One case is when the pipe is insulated by a insulation. So we have to calculate what will be the rate of heat loss from the insulated pipe. And then there is another case where there is a bare pipe. So there is no insulation applied on a pipe. So in that case also we have to find out the heat loss. So by finding the heat loss from the insulated pipe and the bare pipe, we can take the difference between these two, and that will be the saving because of addition of the insulation. So once we get the saving because of this addition of the insulation, then we can at the same time we can also calculate what will be the cost of the insulation, isn't it? And just by looking at these two factors, we can find out how much period will be required to pay back the cost of the insulation in this case. That is what our ultimate aim is. Okay, clear? Now let us look at this problem in more detail. So what is been given here is thermal conductivity is given at point K is equals to 0.9 plus 3 into 10 raised to the power minus 4 into T watt per meter degree Celsius. Okay, so we can solve this problem with this variable thermal conductivity which is varying with temperature, but then our analysis is going to become complicated. So before we can proceed, let us check whether this variation is at all required in this case or not. Okay. So what is being given here is, let me just write down. So K is given here, thermal conductivity is given. So K is given here as 0.9 plus 3 into 10 raised to the power minus 4 into T watt per meter degree Celsius. Okay, this is what has been given. Correct. Now we have to see whether this variation we have to use or we have to use the constant value. Okay, because if you use the constant value, then our analysis becomes extremely simplified. Just wait, I'm just coming. Okay. Okay. Now let us calculate this value of K for the given range of temperature here. So what is the range given? So the maximum temperature here we can have is 160 degrees Celsius because that is the temperature of the steam which is flowing through the pipe, isn't it? And the lowest temperature in this case could be the temperature of the ambient, isn't it? So for these extreme variation, let us see what variation this K value is going to have. So the maximum range of variation in temperature is the maximum range of variation in temperature can be 160 degrees Celsius to 30 degrees Celsius, isn't it? So let us check the value of K at 160 degrees Celsius. At 160 degrees Celsius, K is calculated as 0.9 plus 3 into 10 raised to the power minus 4 into 160, because the temperature in this equation is given in degrees Celsius. You can clearly see. So calculate this value and again calculate at 30 degrees Celsius. So K in this case could be 0.9 plus 0.9 plus 3 into 10 raised to power minus 4 into 30. So calculate this value. Calculate both the values. So what are the values corresponding to 160 and 30? Anybody? So this comes around 0.948 watt per meter degree Celsius, and this comes around 0.909 watt per meter per degree Celsius. Correct? Is it correct? Are you all getting the same value?
Yes, sir.
Yes, sir.
So now based on these values, what we can conclude? We can conclude that even though we are looking at the maximum range of variation of the temperature, but the K value is not varying too much, isn't it? Value of K is at 160 degrees Celsius, it is 0.948, whereas value of K at 30 degrees Celsius is 0.901. So that is kind of 0.91, isn't it? So it's not varying too much, isn't it? So even if we assume a constant value of K in this case, it is not going to affect my answer significantly, because there is no significant variation when we are looking at the variation of temperature from 30 to 160 degrees Celsius, isn't it? Correct. Of course, we can solve this problem with variable value of K, but that is going to make our analysis extremely complex. But just by ignoring that variation, which is reasonable assumption in this case, we can solve this problem easily. Can you see? Can you see that simplification here? Is it all right? Hello.
Yes, sir.
So we can assume a constant value of K. Therefore, I can just write it. Therefore, since K is not varying, much, the analysis can be simplified immensely by assuming constant value of K, constant value of K equals to K average, and that can be given as 0.948 plus 0.909 divided by 2. So this comes around, anybody, 0.929. Is it correct? Is it correct?
Yes, sir.
So
It's correct.
now what is been given here is there are two cases are given. If you read the problem, there is two cases are there. One case is a uh, lagged pipe. That means the insulation is applied on the pipe, and another case is a bare pipe. So I am just doing both these cases separately. So let us have a partition here maybe. Okay. So there is a lagged pipe. So lagged pipe will look like something like this. There is a pipe, and then outside of this pipe there is a insulation. Outside of this pipe there is a insulation, isn't it? Correct. Uh, the heat transfer coefficient here is given H naught, that is given as 5 watt per meter square degree Celsius. This is what is been given, isn't it? Here T is 160 degrees Celsius. 160 degrees Celsius is the T. Here the outside value of the temperature. So that is, let's say this is Ts and this is T naught. So this is given as 30 degrees Celsius. Correct. And this is the insulation. This is the insulation. Correct. There's another case is given where a bare pipe is given. So this is the bare pipe, isn't it? Another case is there where the bare pipe is given. So in case of bare pipe, the outside heat transfer coefficient HB is given, that is 20 watt per meter square degree Celsius. Again, T naught is going to be 30 degrees Celsius, and this is going to be Ts is going to be 160 degrees Celsius. Correct. So these are the two cases given. Now clearly when I am having this pipe, insulated by a insulation, my heat transfer rate is going to be lower, isn't it? So I will have a lower heat loss to the ambient. Uh, in contrast to this, if I am having a bare pipe where there is no insulation surrounded here, in that case I will have a higher heat loss to the surrounding, isn't it? And that difference, if I am going to get it, that difference is primarily because of the insulation, isn't it? So I have to find out whatever the difference in heat loss I am getting, that first I have to convert it in a monetary basis, and then that saving in the heat loss, how much time period it will require for that saving in heat loss to make up whatever the cost of insulation I'm going to incur in this case. That is what we have to find out. Okay. Now in this case there is a let us look at each of these cases. This is a lagged pipe. So this is a lagged pipe. So there is a insulation around it, and this is a bare pipe. Bare pipe. Okay, so there is no insulation. Okay, now in this case, first in order to find out the heat loss, we have to find out the overall heat transfer coefficient, because there will be a conduction resistance present somewhere here, isn't it? In this region, in this insulating layer, uh, conduction resistance is going to be there, so that we have to account. Again, there is a outside heat transfer coefficient is there, so that we have to account. We can safely neglect the conduction resistance offered by a metal wall, which is this particular wall, isn't it? we can safely neglect the uh, the uh, resistance offered by the metal wall, and also we can neglect the convective resistance which will be there because of this HI here, isn't it? Because the steam is flowing through this pipe at a very high temperature, so there will be a higher turbulence is going to be there, and therefore the value of H is going to be very high. And since H is very high, the resistance corresponding to this HI for the heat transfer is going to be much lower compared to the resistance offered by this particular insulating layer, as well as the outside heat transfer, convective heat transfer taking place to the ambience, isn't it? So both these resistances are going to be significantly higher compared to the resistance offered by this metal wall, as well as the resistance offered by the convective resistance offered inside the pipe. Okay, so in this case we can write down the expression for the overall heat transfer coefficient based on the outer surface area. So that can be written directly as 1 by H naught plus R naught ln R naught by Ri divided by Kc. Is it correct? Are you all able to get it? How this equation is coming? Is it clear to everyone what we are doing? Hello? Hello? Am I audible?
Yes, sir, it's clear.
Okay. Okay, so let us calculate this. 1 by U naught is given as 1 by H naught. Now H naught we already know, that is given as 5 plus R naught. R naught is going to be the outer radius. So the radius of the pipe is given as 100 mm pipe is given. So that is the diameter of the pipe, isn't it? So radius will be 0.05, isn't it? And above this particular bare pipe there is a 100 mm thickness of insulation is applied. So what will be R naught? R naught is going to be 0.15 meter, isn't it? So that will be 0.15 ln 0.15 divided by 0.05 divided by Kc value is already given in the problem. So that is 0. We have already calculated the average value of Kc. So that is 0.929. So what is the value of U naught? U naught comes around 2.65 watt per meter square degree Celsius. Is it correct? Is it correct?
So can you please repeat how we got 0.15?
Please come again. How 0.15 is coming? That is the question.
Yes, sir.
Okay, what is the value of the radius? What is the information given in the problem? Let us go up in the problem statement. Okay. 100 mm pipe is given. So this 100 mm is nothing but the diameter of the pipe. So what will be the radius? Inside radius?
All right, so we got 0.5.
0.05 meter. And
Yes.
above this there will be 100 mm insulation applied. So what will be the outer radius?
So it will be 0.05 plus 0.1.
Correct. So that is why it is coming. So this part is 100 and this part is 100. Okay. This entire diameter is 100. So this becomes 100 plus 50, that becomes 150 mm. So that becomes 0.15 meter. Correct? All right.
Yes, sir.
Okay. So now let me just extend this line. Okay. Now U naught we have obtained. So let us calculate the heat transfer. So heat transfer Q for the lagged case is going to be what? U naught, that is the outer, the overall heat transfer coefficient based on the outer surface area into A naught, isn't it? So A naught in this case is going to be 2 pi RL, isn't it? So that will be 2 pi RL. So in this case into 2 into 3.14 into R naught. R naught is going to be 0.15 and assume the length L equals to 1 meter. So this becomes into 1 into delta T. So delta T is going to be what? 160 minus, what is the temperature given? 160 minus 30, correct? So maybe I just write down it. Okay, I will write down it in the, just wait. 2 pi R naught L into Ts minus T naught and assume L equals to 1 meter. Okay. And this is R naught. Okay. So what we are going to get is 2.65 into 2 into 3.14 into R naught is 0.15 into 1 into 160 minus 30. So this is going to give me the total heat loss. So how much is the value? Can anybody tell me?
324.52.
324.52. Okay, right. Clear? Is it clear to everyone? Now, in a similar manner, we can calculate the heat loss from this bare pipe, isn't it? So heat loss from the bare pipe QB, let's say QB. What will be QB? In this case is going to be HB into AB, that is the area of the bare pipe, into Ts minus T naught. So this HB is what? This is the value of HB is given as 20 watt per meter square degree Celsius, isn't it? So that becomes 20. AB is going to be what? 2 pi RIL. So that becomes 2 into 3.14. What is RI? RI is going to be 0.05. 0.05 into length is just 1 meter into 160 minus 30. So this comes out to be, just check whether this is correct. Are you all getting the same?
Yes, sir.
Yes, sir.
Now the difference of these two, so saving in heat loss. Okay. Saving in heat loss will be what? Q bare minus QL, isn't it? So that Q bare is 816.8 minus 324.5, isn't it? So around 492 watt something you should get. Are you all getting the same?
Yes, sir.
Yes, sir.
Now this is given in a watt. We wanted to convert back into rupees, isn't it? Ultimately, we are looking at the rupees, correct? So saving in RS per year, that will be given as what? 492 is in watt, isn't it? So we have to convert it in a yearly basis. So that means 3600, that will be the seconds present in 1 hour, into 24. So that will be day, into, we can assume that there are 300 working days in a year. So 300, isn't it? Correct. Now this saving in the heat loss, isn't it? Saving in the heat loss, whatever we have obtained, whatever the heat loss we are saving, otherwise that will be corresponding to what? That will lead to the condensation of the steam, isn't it? If we don't save this amount of heat loss, the equivalent amount of the steam is going to get condensed because of heat loss to the surrounding, isn't it? So we can find out how much amount of the steam is going to get condensed if we don't save this much amount of heat loss, isn't it? So that we can directly obtain by dividing the latent heat of the steam that is already given. So that is given as 1825 kilojoule per kg is given, isn't it? So that means we have to multiply by 1000. So that is joule per kg. So from this what we have obtained is the mass of the steam that will be saved over the years, isn't it? Mass of the steam that will be, saved over the years because of, avoiding this much amount of heat loss. Are you able to get it? Now we can convert this in terms of rupees because the cost of the steam is given. Cost of the steam is given as 750 rupees per ton is given. So we can calculate per kg by dividing this. Are you all able to get it? Is it clear to everyone? Are you all able to understand what I have done? So this is going to give me around 5240 rupees saving per year. Are you all able to understand what we have done here? Yes, no, please. Hello.
Sir, can you explain
it again?
Yeah, latent heat part.
Okay. So we obtained the 492 watt as a saving, isn't it? When I am using a insulated pipe instead of a bare pipe, isn't it? Correct?
Yes, sir.
Yes,
Now
sir.
this insulation, because of this insulation, 492 watt is saved. If I don't use the insulation, what will happen? This much amount of heat loss is going to be there additionally, isn't it? If I don't use a insulated pipe. So definitely heat loss to the surrounding is what? Corresponding amount of steam is going to get condensed, isn't it? Because the heat is supplied by the steam, isn't it? So that much amount of steam is going to get condensed. So from this 492, we have first obtained how much amount of heat will be saving, how much amount of the heat loss will be saved over the year. So for that, what we have done, this is given in a watt, isn't it? So now we have to convert it in yearly basis. So what we have to do is first we have to multiply 3600. So that means this much amount of, this many seconds are present in 1 hour multiplied by 24 hour into 300 working days. So that is going to give me the total amount of heat loss saved over the years. Now this much amount of heat loss which we have saved over the years, I wanted to find out what will be the equivalent amount of steam, because this much amount of heat loss otherwise would have resulted in the condensation of the steam, isn't it? So the latent heat of the steam is given 1825. So I have just divided latent heat of steam 1825 and that is given in kilojoule per kg. So that is why I have multiplied by 1000. So this bracket is going to give me the amount of steam that would have, condensed if I wouldn't have, saved this much amount of heat loss. Is it clear? Is it clear?
Yes, sir.
Now amount of
Yes.
steam condensed I have obtained. Now I can convert that into a rupees because the cost of the steam is already given. Cost of the steam is given 750 rupees per ton. So that I have multiplied 750 divided by 1000. The 1000 is because there it is given per ton. So I have converted in per kg, isn't it? So this is going to give me the amount of rupees that I am going to save over the year if I avoid this much amount of heat loss by adding a insulation. Is it clear now to everyone?
Yes, sir.
Yes, sir.
Now let us look at what will be the cost required for insulation. So cost required for the insulation, the cost factor is given, that is 15,000 rupees per meter cube is there. So that is per meter cube is there. So first we have to find out how much amount of insulation will be required to have a 100 mm lagging around the bare pipe, isn't it? So volume of the insulation we have to first calculate. Volume of the insulation. So volume of the insulation is given as pi r square, that is we have to subtract. So this is the volume, this is nothing but the area of the lagged pipe minus, if I do 0.05 square, so this is the area of the bare pipe I have subtracted, and multiplied by length L equals to 1, so that is going to give me the volume, isn't it? So this comes out to be how much? Anybody? This comes out to be 0.0628 meter cube. Check whether this is correct.
Yes, sir.
Yes, sir.
Now we can convert in terms of the cost. So cost of the insulation is this volume multiplied by the cost factor, so that is 15000, isn't it? So this comes out to be 942.5 rupees, isn't it? Now what is the question? Question is how much time period will be required to pay back this insulation cost. Now here insulation cost is 942, whereas the saving is 5240. So saving is much higher compared to the cost required for the insulation, isn't it? So we can directly calculate the payback period. Payback period can be directly calculated as the cost of insulation by saving, isn't it? So this becomes 942.5 divided by 5240. So this comes around 942.5 divided by 5240. So this is coming around 0.1798 year. So this is equivalent to 2 months. Is it clear? So payback period is around 2 months. Again, one more point to note down here is, for finding out the payback period, we have directly, took the ratio of cost of insulation by saving. We have not incorporated here the interest rate, because the saving is much higher compared to the cost of insulation. Therefore, even if we don't include the interest rate, doesn't matter, but otherwise the correct expression is what? Correct expression is this. This is, let's say, if I denote this as P1 and if I denote this as, let's say, P2, the correct expression in this case should be payback period will be P2 divided by summation of J equals to 1 to N P divided by 1 plus I raised to the power J. This should be the correct expression. P1, this should be the correct expression, but we have ignored this interest rate in the above expression, because even if you include this, it doesn't matter. It is not going to vary too much. Are you all able to get it?
Sir, can you explain the payback period formula once again?
Have you seen the class notes last?
Yeah. Yes, sir. Yes, sir.
Just wait. Let me open that for you. Transfer coefficient. So in fact that we have already covered in the last class. So if you look at there, you will clearly understand why I have done this. Okay, just wait. Let me just project. Can you see the presentation?
Yes, sir.
Okay. So see here what we have done is, can you see from where this is coming? Hello?
Yes, sir. Yes, sir.
So this is basically what, remember here the insulation, whatever the insulation you are having, that will have some, that insulation will have the life, isn't it? So that life of the insulation is, let's say, n year, isn't it? So this summation has to be over the life of insulation. Okay. This summation has to be over the life of insulation. And also the important point here to note down is, see, when you are purchasing the insulation, you have already invested something. So you are going to pay a interest rate on that. Isn't it? You are paying the interest rate on that. But whatever the saving in the hit loss is coming, saving in the hit loss is coming, that is you are kind of making up that particular thing over the year, isn't it? So therefore this 1 plus I raised to the power j comes in the denominator of this saving. So here this 1 plus I raised to the power j, this basically accounts the compound interest. This accounts the compound interest. Can you get it?
Yes, sir.
Okay. Okay. So let us go back to our tutorial again. Let me just project. So we will extend, I think 5 or 10 minutes today. So do you have any more tutorial after this?
Sir, I had a doubt.
Please go ahead.
Yes, sir. Sir, I wanted to ask, in the critical insulation thickness, we consider T naught as the ambient temperature. But sir, when I tried to do it from the scratch by considering the two Qs separately, the heat rate that is caused due to conduction and the heat rate that is caused due to convection. If we will take T naught as the ambient temperature and same for the outer temperature of the pipe.
Just wait. Your 1 minute. Vishruta, can we discuss it after this tutorial?
Yes, sir.
Let us complete this tutorial, and whoever has some doubt, we can extend after that. It's perfectly all right.
Yes, sir. All right.
Okay. So let us complete this tutorial first, and then we will come back to your doubt. Okay. Okay. So let me now this is the answer for the first part. Let us look at the second problem. Okay. So let me just copy again the statement of the second problem, and then we can continue. Okay. Just wait. Okay. Now what is been given in the second problem is there is a water at 25 degrees Celsius flows over a wide hot plate at 1.5 meter per second free stream velocity at a zero angle of incidence. The plate is 1 meter long in the direction of flow. Determine the local and average heat transfer coefficients. Calculate the heat supply necessary to maintain the plate at 70 degrees Celsius. Heat flow occurs from one side of the plate only. The laminar part of the boundary layer is given by Nusselt number is equals to 0.332, Reynolds number raised to the power 0.5, and Prandtl number raised to the power 0.333. Similarly, the turbulent part of the boundary layer is given as 0.0296 Reynolds number raised to the power 0.8 and Prandtl number raised to the power 0.33333. Okay. So again here, when I copy the problem statement from my tutorial sheet to this MS, this whiteboard, these superscripts are getting messed up. So you please follow the actual tutorial sheet which I have uploaded. Clear? So just for the continuity purpose, I generally copy the problem statement here. Okay. So what is been given is, if you look at the problem is something like this. There is a just wait. Right. My drawing is extremely lousy, so please bear with me. I will try to do it in a better manner. Okay. Okay. And then there is a free stream velocity. So free stream velocity is given as 5 meter per second, isn't it? And let us say this is my boundary layer. This is my boundary layer, isn't it? This is my boundary layer. Okay. This particular length is given, that is 1 meter is given. This particular length is given as 1 meter, isn't it? Now, in addition to this, what is being given in the problem is temperature here is given. So T naught is given as 25 degrees Celsius and the temperature of this plate is given. So temperature of this plate is given. So that is TS is given as 70 degrees Celsius. Correct. So this is what is been given here.
So velocity is 1.5.
Huh?
So the velocity given is 1.5. Free stream.
Velocity is given as just yes 1.5. Sorry. Velocity is given as 1.5 meter per second. Okay. Now what is been asked in this particular problem is we have to find out the local heat transfer coefficient and the average heat transfer coefficient. Now, first thing which we have to decide here is whether this entire region of 1 meter is going to have a laminar zone or whether it is going to have both laminar as well as turbulent zone. Isn't it? That we have to first find out, isn't it? Because remember in the boundary layer, in the boundary layer, initially the boundary layer is in a laminar zone, then it is going in a transition zone, and then after that there is a turbulent zone, isn't it? In this case we are assuming that there is only a laminar and a turbulent zone, there is no transition zone, so even transition zone is considered as a turbulent zone. Okay, but what we have to find out is for the given length of 1 meter whether I am going to have only a laminar zone or both laminar plus turbulent zone. That I have to find out. So, so how we can find out? We can find out just by obtaining the maximum value of the Reynolds number, isn't it? So what will be the Reynolds number at this location? At this location, what will be the Reynolds number here? If I find out at this location, then if this Reynolds number is less than the critical value of the Reynolds number, the critical value of the Reynolds number is given as 5 into 10 raised to the power 5, isn't it? So beyond that, the turbulent zone starts. So if my Reynolds number is less than 5 into 10 raised to the power 5 at the end of this particular plate, then I am sure that only the laminar zone is present. If the Reynolds number corresponding to this location on the right hand side, if comes to be greater than 5 into 10 raised to the power 5, in that case it's a clear indication that we are going to have both laminar plus turbulent zone, isn't it? So that we have to first find out. Now what is been given here is the temperature is 70 degrees Celsius and the free stream temperature is 25 degrees Celsius and the fluid which we are looking at is a water, correct? So the properties of the water first we have to, find out. So properties of the water are given in the back side of the book. So properties of the water we have to find out. Okay. So properties of water are given at the back side of the book. If you look at the back side of the book, the properties of the water is given, and water as well as air both are given as page number 518 and 519. So at page number 518 the properties of air are given, whereas at page number 519 the properties of water are given, isn't it? Again, in the properties of air there is one more mistake in the table. The value of momentum diffusivity is given as, please write down, value of momentum diffusivity is multiplied by 10 raised to the power minus 6 in the table. So instead of that 10 raised to the power minus 6, that is 10 raised to the power minus 5. That is the mistake. Okay, please correct that. So momentum diffusivity into 10 raised to the power minus 5 should be the correct thing. Okay, please correct for the air. For water everything is correct. Okay, so now properties of the water we have to obtain. The question is at what temperature? The question is at what temperature? Because the temperature here is, free stream temperature is 25 degrees Celsius. The temperature of the hot plate is 70 degrees Celsius, isn't it? So which temperature we have to use? Are you getting the point? So temperature in such cases is taken as an average temperature, isn't it? So average temperature in this case is going to be what? T average is going to be 25 plus 70 divided by 2. So that comes out to be 47.5 degrees Celsius. Okay. So why we have taken the average temperature? Because at the adjacent to this particular plate, the temperature is 70 degrees Celsius. So the properties are going to be different here. But if I look at the properties very close to this free stream velocity here somewhere, there the properties will be corresponding to 25. So better option here is to average temperature and take the properties all at the average temperature. Otherwise we have to look at the variation in the properties as well in addition to our analysis. So that we have avoided here by using the average temperature. Okay. So properties of water at properties of water at 47.5 degrees Celsius are given as, I will just quickly write down. This is from the tables given at the back side of the book. So rho is 989 kg per meter cube. That is what you are expected to get. Mu you will have 5.77 into 10 raised to the power minus 4 kg per ms. Specific heat is given as 4180 joule per kg per degree Celsius. Thermal conductivity is 0.64 watt per meter degree Celsius, and Prandtl number you are expected to get is 3.77. Okay, now these are the properties we have obtained. Now we have to find out at x equals to L equals to 1 meter. Find out the Reynolds number maximum. Maximum Reynolds number will be at this end, isn't it? So that can be given as LV rho by mu, LV rho by mu. So L is 1 meter, V we have already given in the problem, that is 1.5 into rho is 989 by mu is 5.77 into 10 raised to power minus 4. So this comes out to be 2.57 into 10 raised to the power 6, isn't it? Is it clear to everyone? Hello? This white screen is visible to everyone? Whiteboard is visible?
Yes, sir, it's visible.
Okay, so now this RE max, the RE max, the Reynolds number, maximum Reynolds number is greater than RE critical, isn't it? What is the value of the critical Reynolds number? Critical Reynolds number is 5 into 10 raised to the power 5, isn't it? That is what we have seen in the last class, isn't it? When Reynolds number is less than 5 into 10 raised to the power 5, then my flow is laminar, isn't it? But here at the end of the plate, my maximum Reynolds number comes out to be greater than 5 into 10 raised to the power 5. That means both laminar and turbulent zones will be present.
Hello, sir.
Yes.
So the mu is given as 5.77 into 10 raised to 1 minus 3.
Where?
Sir, in the table only.
Just let me check. At the value of the temperature is 47.5, isn't it?
Yes, sir. So 320 Kelvin.
Around 320. So mu is 5.77 into is it correct? It's not correct. It seems to be correct. Just check.
Sir, in my column, it's given on the top to multiply by 10 raised to 1 minus 3.
Correct.
Minus 4.
But that is the value comes out to be 0.577. Here I have written 5.77.
Oh, yes, sir. Okay.
So this is correct, right?
Yes, sir.
Okay. So only problem is there with the table of air. So there this diffusivity, thermal diffusivity value that there is some correction. Okay, that I have already notified, isn't it? Other than that, for water the properties are given correctly. Okay, anyway, so now this Reynolds number is greater than the critical value of the Reynolds number, that is 5 into 10 raised to the power 5, and therefore I will have both turbulent as well as laminar regions. Again, we have said that in the starting itself there is no transition zone. So even transition zone we are considering in a turbulent zone. Okay, clear? So now let us find out up to what length we will have a laminar zone. Up to what length from leading edge we will have laminar zone. That we have to find out. So how we can find out? We can just put the Re critical. So that becomes 5 into 10 raised to power 5, and that is given as LC, which is the critical length, into V into rho by mu. So we can put LC as it is into 1.5 into 989 divided by 5.77 into 10 raised to power minus 4. So this comes out to be, from this LC comes out to be 0.1945 meter, isn't it? So what it means is if we look at this particular figure, it means that between this length, which is LC equals to 0.1945, we will have laminar zone, and after 1945 to 1 we will have turbulent zone, isn't it? Is it clear? Is it clear to everyone? Yes, no?
Yes, sir.
So now our job becomes simple. Now we can use the correlations given in the problem, and we can find out the local heat transfer coefficient. So for laminar zone, For laminar zone, I can write down, maybe I can write down this. So Nusselt number is given as 0.332 Reynolds number raised to the power 0.5 into Prandtl number raised to the power 0.333, isn't it? So this we can write in terms of the actual variable, so that becomes h dash x by k. H dash is nothing but the local heat transfer coefficient in a laminar zone, and that is given as 0.332 into Reynolds number in this case is going to be x v rho by mu 0.5 into Prandtl number raised to the power 0.333. We can put all the values here. So h dash x divided by k is given as 0.332 into x raised to the power 1 by 2, and I can put v and rho. V is 1.5, rho we are already seen that is 989 divided by mu is 5.77 into 10 raised to power minus 4 raised to the power 0.5. Prandtl number is 3.77 raised to the power 0.3333. So this comes out to be 828.2 x raised to the power 1 by 2. Okay, now we can put the value of h k here. So k is 0.64, isn't it? 0.64 is there. So this becomes h dash x by 0.64 equals to 828.2 x raised to the power 1 by 2. So this gives me h dash is obtained as 530 x raised to the power minus 1 by 2. So this is the local heat transfer coefficient, and this is valid in 0 to 0.1945. In this region it is valid, isn't it? So this is the local heat transfer coefficient in the laminar zone. Similarly, the local heat transfer coefficient in a turbulent zone we can calculate. Okay, just wait. So local heat transfer coefficient in a turbulent zone. So in a turbulent zone, again the correlation given was Nu, that is the Nusselt number is given as 0.0296 Reynolds number raised to the power 0.8 into Prandtl number raised to the power 0.333. So this again we can simplify as 0.0296 into x v rho by mu 0.8 is there, isn't it? So that is just 4 by 5. So we can simplify this Prandtl number 0.333. We can further simplify this as h double dash x, where h double dash is nothing but the local heat transfer coefficient in a turbulent zone divided by k, and that is equals to 0.0296 into x raised to the power 4 by 5. Here I can put the value 1.5 into 989 divided by 5.77 into 10 raised to power minus 4, and this is again 0.8. Prandtl number is 3.77 into raised to the power 0.333. So what we get from this is h double dash is obtained as I'll just write down the final expression 6184 x raised to the power 4 by 5, and this can be represented as h dash x divided by k. K is 0.64, isn't it? So from this we can simplify and we can find out h dash as 3958 x raised to the power minus 1 by 5, and this is valid. This is a local heat transfer coefficient, and this is valid in the region 0.1945 x1. In this region it is valid, isn't it? Correct? Is it correct? Are you all able to follow? Hello? Hello?
Yes, sir.
Okay. So now these are the local heat transfer coefficient. Now we have to find out what will be the average heat transfer coefficient, isn't it? So average heat transfer coefficient we can directly obtain by integrating both these. So average heat transfer coefficient is H average can be obtained as 1 by L, that is the length of the tube, length of the plate, and this is 0 to LC H dash dx plus LC to 1 H double dash dx. This expression we have to solve in order to find out the average value of the heat transfer coefficient. So we can directly put all the values here. So 1 upon L, length of the tube, length of the plate is just 1, so that becomes 1. This is 0 to, this becomes 0 to LC, that is 0.1945. H dash we have already obtained, that is 530 x raised to the power minus 1 by 2 dx plus 0.1945 to 1, and H double dash we have obtained as 3958 x raised to the power minus 1 by 5 dx, and we can solve this integral, both this integral. So what we get after solving both this integral is what we obtain from this integral is 530 into 2 in the bracket x raised to the power 1 by 2 and 0 to 0.1945. This is the first factor. Second factor is 3958 into 5 by 4 in the bracket x raised to the power 4 by 5, and this is 0.1945 and 1. So what we get from this is H average. H average is 4083 watt per meter square degree Celsius. So is it clear? So just we have integrated over the length and we have obtained the average value of the heat transfer coefficient. Is it clear to everyone? Hello? Hello?
Sir, I had a doubt.
Okay, go ahead.
Sir, the H we have found, the local H value, sir, not the same at the boundary.
I'm not able to understand what you are trying to say. Please go.
The value of LC, that is 0.1945 in X for the first expression, the laminar region and then in the turbulent region. So they're different. So sir, aren't they supposed to be same on the boundary?
So these are coming out to be same at the boundary, isn't it? No, it's not coming.
Sir, I calculated, then it is not.
These are not coming. So
No.
that could be because, see, that could be because we are using a different expression, different empirical expressions to calculate this, isn't it? We are using a different expression, and in fact this expression is valid in the turbulent zone. This is not valid in a transition zone. Remember, there is a transition zone in between.
Yes, sir.
But that we have neglected here, isn't
right,
it?
Sir.
So that anomaly coming primarily because we have neglected the transition zone, and that is why there is no smooth, increase in the transfer coefficient.
All right, sir.
Okay. Okay, so now our job becomes easy once we get the average value of heat transfer coefficient, because ultimately what we are interested in how much amount of heat we need to supply continuously to the plate in order to keep the temperature of the plate exactly at the 70 degrees Celsius. So what it means is, let me just go up and explain you again. What is exactly we are looking at is, just wait. Okay, so now suppose this is the plate which is at the 70 degrees Celsius. So if we don't supply continuously the heat to this particular plate, what will happen? Eventually the heat will be dissipated to the fluid and eventually the temperature of the plate is going to decrease, isn't it? If we don't supply. But the question is how much amount of heat need to be supplied continuously to this plate in order to maintain this plate exactly at the 70 degrees Celsius. So at a steady state, what will happen is whatever the amount of heat that being supplied to this particular plate should be same as the amount of heat dissipated from this plate, isn't it? Then and then only the temperature will be maintained at 70 degrees Celsius. Are you able to get it? What I'm trying to say? Hello? Is it clear what I'm trying to say?
Yes, sir.
So that means the amount of heat that need to be supplied here should be same as the amount of heat that is being dissipated from the plate. So here we can directly calculate the amount of heat that being dissipated from the plate just by putting the Newton's law of cooling directly here, isn't it? So that will be the same as the amount of heat that being supplied to the plate continuously, correct? So the last part becomes easy. So amount of heat that need to be supplied, amount of heat that need to be supplied to the plate to maintain its temperature constant at 70 degrees Celsius should be same as heat dissipated. So Q directly can be obtained as HA delta T directly, isn't it? So H in this case we have already obtained average value of heat transfer coefficient. So that is H average. I just write average. So this becomes 4083 into area. So length of the tube is given. Let's assume that the breadth, breadth is also 1 meter. So this becomes 1 into delta T in this case is going to be what? 70 minus, what is the temperature? Ambient temperature? The ambient 25, correct. So that becomes 25. So what is the value? Anybody? Hello? What is the value?
183.
735.
183735 watt. Okay, correct. So this much amount of heat need to be supplied continuously to the plate in order to maintain the temperature of the plate exactly at the 70 degrees Celsius, correct? So this is all about the tutorial. Okay. So we stop here unless you have any doubt, and then we will, look at the individual doubts if anybody is having. Okay. Hello. So can we stop here? Hello. Okay. So what was your doubt, Vishruta? Hello.
Yes, sir. Sir, I think I'll have to share my screen for that.
Okay, go ahead. Let me stop this recording. Then you can share. No problem. Okay, let me stop this.